Hello and welcome back to Integrated Science. Today we're going to talk a lot about the idea of our solar system. So previously we've talked about measurements and we introduced our astronomical unit, the distance from the sun to the earth, and all those measurements that kind of go in between, such as light year and parsec. And then obviously we still have our kilometers. So we're going to be looking at a couple of different things today, mostly talking about the history of our solar system and two very important gentlemen, Copernicus and Galileo, and their contributions to how we think about the movement of our solar system today. And then we'll get into the idea of where did this all come from and how did gravity play a role in this, which is called the nebula theory. So up until about this unit, we have mostly been talking about laws and been able to mathematically prove how to find speed, how to find kinetic energy, how to find potential energy and work. Now we're kind of moving into that section of the year where we're starting to talk about theories and ideas. We can back a lot of theories with some of the concepts that we learned. So for today, for example, we are still going to talk about speed. We're also going to talk about gravity, not the same kind of gravity that we used in our potential energy at 9.8 meters per second, but we're talking about the big G of gravity, meaning how if we think about distances, how gravity can be affected if objects are closer together and further apart. So kind of piggybacking off of our idea of magnetism and electricity is that the closer you have two objects together, the more of a force that is between them. And that's the same thing with gravity. Gravity of the sun and Mercury is much stronger than the gravitational pull of the sun and Saturn. So we'll talk about how that kind of works and all comes into play. And remember, mass has another important aspect that has to do with gravity too. The more massive an object is, the stronger the gravitational pull is going to be with that. So go ahead and jump into Canvas, or if you want to go ahead and get out a sheet of paper just to get down some notes on our two different modes of how we have looked at our solar system. One is called the geocentric model, one is called the heliocentric model, and then we're going to talk about the nebula theory. So I'm going to jump down into our space unit here, and I'm going to move into planets and solar system formation. So I'm going to pull this up, and I actually already have it here for us. Just going to slide up, and let's go ahead and get started. So one of the first earliest observations in science and things written down was actually more for astronomy. People have always looked up at the night sky and wondered, what are these objects that are beaming light at us or twinkling? And so there's been all these different hypotheses and ideas, and it starts way back with even our early ancient Greeks. If you end up taking astronomy, we'll talk about Stonehenge and early calendars and how people really use, or I should say civilizations really use the motion of stars in the night sky to help figure out when to plant crops, when to harvest those crops, when to hunker down because winter's coming, or when to plant the seeds because spring is about to arrive. So all of these actually had to do with just them mapping out the stars. We'll even do a little bit of talk more when we get to the star section about constellations and their importance to what we kind of know about our solar system and universe, as well as our closest star, the sun. We will talk in great detail about and its significance, importance. But to the naked eye, way back in early time, there was a gentleman named Aristotle, and Aristotle was a scientist by many natures, but one of the things that he really did try to predict and kind of understand was just the idea and the motion of what he thought were all stars. Later to find out some of the stars that we see actually are planets. You can visibly see Mercury, Venus, Mars, Jupiter, and Saturn, depending on the time of year, but they are visible. If you're curious about it, ask me about an app. It's called the Sky Map, and you can hold it up just to the night sky, and it will point out all the constellations, and you can normally see those planets. It will point out what you might think is a star is actually a planet. They're normally the first ones to pop up in the evening sky too. They are very luminous, very bright. They are not generating energy. They're actually like big mirrors and they're reflecting energy. Same thing with the moon. The moon is like a huge mirror. It's actually not producing any energy at all. It's just reflecting the sunlight off of its surface and beaming it out to us. So Aristotle, though, he was the first one to kind of write down and kind of preach about the idea that the earth was the center of the universe. And as you can see from the picture here, he placed Earth in the center and then went out with the moon, Mercury, Venus, the sun, Mars, Jupiter, and Saturn. And this is called the geocentric model. So think like if you're studying geology, it's earth-based, it's rock-based. So he put the earth in the center. So his hypothesis was that they all orbited around in a perfect circle. And we're going to debunk all of this because unfortunately Aristotle was not correct at all. But he made observations and it was accepted for a long time. But other astronomers that came after Aristotle started to really map the way the stars moved in the sky. So think like the sun comes up in the east and sets in the west. Same thing with most of the stars. However, there were several of them that did this loop-de-loop in the night sky, meaning that when you would map it out night after night, it didn't go in the nice arc across the night sky. It went in these loop-de-loop patterns. And this is what we call retrograde. And it actually isn't stars, because all stars actually do arc across the night sky. These were some of our planets. So Mercury, Mars, Venus, the ones that have closer distances from the sun, or I should say in between the sun and the earth, they don't have that nice arc pattern because we're seeing something completely different. So what we're seeing is retrograde, meaning that we're seeing it kind of move in one direction and then it kind of goes back the other way because it's moving around the sun faster than the earth is moving around the sun because its orbit is much smaller. So anyway, there was people that hypothesized just about Aristotle and then were like, well, this doesn't make complete sense. So lo and behold, comes Copernicus. In 1543, he came up and proposed the model of the heliocentric model, and helio for helium, and that's what the sun is producing. It is fusing together, and we'll talk a lot about this soon, fusing together four hydrogen atoms, and when it fuses 4 hydrogen atoms together, it produces helium. So heliocentric, the sun is producing helium. And so he mapped out the night sky as well and was puzzled by this retrograde, that circling of some of the planets in the night sky. And he's like, this doesn't make any sense. So he started rearranging and started doing math and algebra and started to come up with these ideas that, no, this isn't right, and decided to reorder the distances and the positions of the planets and ended up putting the sun in the center. And he called this the heliocentric model. Once again, you can see that he still has this circular pattern that is the orbits of the planets, and we'll talk about this circular motion is not absolutely correct. It's more of what we want to call an ellipse or an oval, and we'll talk about that. But to this day, we still believe in the heliocentric model. We can actually now prove it. We have satellites orbiting all of the different planets, as well as we actually have a satellite that has gotten the closest it's ever been to the sun. That was launched back in 2008, and we'll talk about that here in the near future as well. And so we're able to actually visibly see that motion and visibly look and say, okay, everything else, the patterns are now orbiting around the sun. So geocentric model no more, heliocentric model rise. So As we move forward, though, we're going to start talking about these terms or objects in the night sky. And so, once again, I want you to think of the idea of the law of conservation of energy. Is that energy is not created or destroyed, it's just transferred back and forth, back and forth, back and forth. And we proved that with our roller coasters. Same thing with matter. Matter is not created or destroyed, it's just transferred back and forth, back and forth, back and forth. And we talked a little bit about this with Einstein and his equation of E equals mc squared. And he was able to say if energy can move fast enough, it can create matter, and matter can produce energy. And that's that linking part that we've kind of discussed. So now we're really going to be looking at that idea of matter going into energy and energy and going to matter. So one of the building blocks of the whole universe are these objects called a nebula. And a nebula is a cloud of gas and dust. And some of them can hold the proper matter to create different types of objects in what we see in space. Some nebulas are going to create stars, depending on if it has a whole bunch of hydrogen available. Some nebulas might have heavier elements, which then can create other planets or solar systems. And this is actually proven. There are several hundreds of other exoplanets orbiting other stars, very similar to our sun. Some are much bigger, some are much smaller. You can even look at, if you think about, if you've seen Star Wars, in The New Hope, there is a scene where Luke Skywalker is looking at a double sunset and he's on a planet orbiting around it. So there's a lot of strange things happening in space, and we're going to start kind of discussing those ideas that you can have what is called a binary system, which is what Luke was looking at, two stars and then a planet's orbiting around there. Same thing if you've ever seen Avatar, is that you could see the different objects that were much closer and further away. That was a system that would maybe be something if we were to orbit around Saturn. So we'd have smaller rings, and Saturn and Jupiter both have, on any given day, up to 100 moons around it. So Avatar kind of mimics that idea behind it too. So a nebula is kind of like the nursery for other things to form or evolve. And so we'll talk about these different nebulas and what we can see with them. But the definition is just a model of formation of a solar system in which the sun and planets condense from a cloud or nebula of gas and dust. So what happens with nebulas is that how a nebula forms, let's even go there just a little bit. So when a star reaches the end of its life, it has a couple of different options depending on its mass. Most of the time, depending on its mass, if it's a really, really large star, it's going to do one or two things. It's going to either explode and turn into a supernova, which then leaves a nebula, or if it's much bigger, it will turn into a black hole and implode on itself, and we'll talk about that more. If it's a smaller size star like our sun, it will not explode. It's just going to kind of poof outwards just ever so lightly and then leave a cloud of gas behind, another nebula, and the core will just slowly cool off. It's not as very exciting as a massive star, but our sun is a much smaller / medium-sized star. So what happens is that in these larger nebulas, there's a lot of matter. And if you have a lot of matter, you have a lot of mass. And if you have a lot of mass, you then have gravity. And so gravity wants to pull everything back in. And that's exactly what this is happening, what we call accretion. This is a term we'll use quite a bit. So planets form after a nebula starts to spin and the particles of matter collide. We call this accretion. And so these are the 7 steps of a nebula, and we're going to talk quite a bit about this, as well as I'm going to have you watch a video over Crash Course with it. But we start out with a nebula. The nebula starts to kind of collapse and spin in on itself. That's our accretion. And those clumps of matter are going to run into each other, kind of think of like Play-Doh, and get bigger and bigger and bigger until they start to form small planets. And then those small planets are going to collide and form bigger planets. And then normally a star somewhere in the center is going to be born, or created, I guess I should say, start burning hydrogen and helium, and then it causes even more gravitational pull. And so that's what this picture is kind of showing here. Nebula, accretion, small planetesimals. We've got a star starting to form, more organized, and finally super organized. I hope this helped, and we'll see you again soon.